Welcome to Robustness Hands-On Tutorials Part 1. Today we will be discussing about distribution shifts and data poisoning, specifically Trojan attacks. So to introduce you to robustness is basically the ability of AI systems to maintain their performance and reliability under a wide range of conditions. Now, these conditions may be noisy data, unforeseen extreme events, or adversarial attacks, or poisoning attacks, like we will be discussing soon. So to start off, let's talk about distribution shifts. These are the main common type of errors which occur when you deploy a machine learning model. A distribution shift is basically when the input and output differ in their distribution. Pretty obvious, right? But what exactly do we mean by that? So the training distribution is not similar to the testing distribution. Uh, An example, a live example is over here. So let's say you train a model to learn numbers and then you present it to your friend saying that, oh, my model can classify numbers. But when your friend tests it on Roman numbers, it fails. Obviously, right? Because you never train it on Roman numbers. And there's a clear distribution shift into the training and testing data. Now, the most common way to deal with this is stress testing. So what I'm showing you here is an image of a bird, but while adding multiple noises to the bird. So if I train an image classifier, it should ideally be able to classify this image as a bird in all of these noises. This is stress testing. Basically, you are taking your training data and imposing it on a lot of different distributions, and you expect your model to work on all of these distributions, right? So let's simulate one of these very simple examples. Okay, so I will be using PyTorch for this tutorial. This is just running basic imports, and I'm just setting my CUDA environment. Now, so the dataset I'm going to be using is called Fashion MNIST. If you do not know what Fashion MNIST is, it's basically a training set of 60,000 samples and like training samples and 10,000 test samples, where each example is a grayscale image and there are 10 classes of images. I will tell you what exactly that means. Basically, these are fashion items, and there are 10 classes of these items. Uh, so if I just visualize the data over here, it's basically just garments, and each of them have a class. For example, boots has a class of 9, and shirts have a class of 0, and skirts have a class of 3. Basically, just a very simple classification data set. Now, what we will try to do is simulate a very simple stress test. Now, if you look at this column over here, what I'm trying to do is inverting the images. Now, since these are grayscale images, what I'm simply trying to do is uh, change all the white pixels to black pixels and black pixels to white pixels, basically just inverting the image. So how I'm doing this is using a lambda function over here, where x represents the pixel value, and I'm just replacing it with 1 minus x. What that means is black becomes white and white becomes black, because from 0 to 1 is your grayscale, and I'm just inverting the grayscale. And I'm just downloading this data set from PyTorch datasets, and this is the command to do that. Uh, so now when I visualize this, something interesting happens, right? Like just the images are inverted. You have all the garments in black now instead of white. It's very simple. Now, what I'm going to do now is train a network on on the training data that we just created and test it on the original fashion MNIST data. So this is the code for a simple neural network. What is happening over here is that I'm initializing my network over here, and I'm just passing the number of classes, which is 10 in this case because Flash and MNIST has 10 classes. Now, this is my neural network code where I start with an initial linear layer of 28 cross 28 because that is the input dimension. And this 256 is just an intermediate uh, neural network output. It could be anything, whatever you wish, but this turns out pretty well. So that uh, after that, there's an activation layer, which is ReLU. And then there's another linear layer which just goes from 256 to 128. Again, these can be arbitrary values. And another activation layer in between, after which there's another linear layer from 128 to the number of classes, 10, because we want our neural network to finally classify the images from which are 10 classes, right? So this is just the forward function which tells you what to do when there's an input, which is x. So all I'm doing is I'm viewing it in a shape which is 28 cross 28, and I'm just passing it through the neural network, which is self-made. That is the neural network that we have. So yeah, this is our neural network. Pretty simple, pretty straightforward. Now I'm constructing an evaluate function, which takes in a PyTorch data loader and the model as inputs. Now, if you want to know what a PyTorch data loader is, I would strongly recommend you check the document. But in a gist, it basically loads your data set into chunks uh, so that your model can train on those chunks instead of the whole data set at once. I'm also using it for evaluation over here just for the sake of ease. Now, what is happening over here? So I'm just trying to calculate the accuracy mainly, but also logging the loss. So I'm just enumerating through the data loader and loading the batches of data that I want to see, which is X and Y, batch of X and batch of Y. And I get the outputs of the model by passing the batch of X into model, which will give me my outputs from whatever model I've trained, right? And this is where I'm computing the loss. I'm using cross entropy for this because this is a classification task. If you want to know what cross entropy is, again, I would strongly recommend you check the PyTorch documents. But um, so essentially, what it computes is how different is the model output from the actual predicted output, right? That's what we want to know when we're calculating a loss of a neural network. So yeah, now I'm just aggregating the loss and also the accuracy. Now, how am I getting the accuracy? I'm just taking the maximum of whatever output I get from the neural network, maximum of the vector, which means since there are 10 classes, whichever whichever item in the vector gives me the maximum value is the class that I'm predicting. And this is what I'm taking as the model output and just checking the accuracy with the actual output. So this is just my evaluation function. Now, this is the code for training the model. Uh, Very simply, what I'm doing here is initiating a train data loader. Again, this is a PyTorch data loader, which basically just chunks the data set for you in batches and gives it to you. And then there's a test loader, and then there's an inverse test loader. So what is this inverse test loader? This is basically just loading the whatever data we have just created, which is inverted data, right? So that's why the inverted test loader. Now I'm declaring an optimizer. I'm using Adam for this because it's pretty standard, and also a scheduler. But you can ignore that. This is, but yeah, feel free to check it out. So what is happening in this code? Uh, so first, what I'm doing is I'm calculating for each epoch. I'm first just calculating what the model evaluates. At this point, what is its loss and accuracy? And the same with the inverse loss and accuracy. Inverse loss in this case is basically how much loss and accuracy it has on the inverse test data. Now, what I'm doing is I'm just going through the train data, again, getting the batch of inputs and outputs and the outputs of the batch, and then calculating the loss. And now this loss is used for backward propagation, which is loss dot backward. And what happens is that the neural network has essentially made a step of learning over here. Uh, if you already know all the PyTorch basics, please feel free to skip. I'm just going through every part. So now I just calculate the loss, and then this is happening in every batch, every epoch, and the model is basically learning. Now, again, at the end of all of my epochs, I'm again just evaluating the model. So if we run this, you will see exactly what I'm just trying to say. Uh, yeah. So here is where I'm loading my model and also training the model. So what happens? So yeah, epoch one, there's a test loss, which is pretty decent, and then there's a test accuracy, which is 0.1, which is basically 10% accuracy, which is random accuracy since you have 10 classes, right? And it starts with 0.1 for the inverse test accuracy as well, because again, random accuracy. Basically, the model has not learned anything at this point, which is pretty obvious. What happens when in epoch one, uh, the model learns and it becomes 83% accurate, and then this keeps increasing for the test accuracy. On the other hand, the inverse test accuracy remains the exact same. In fact, it gets a bit lower than random, which is pretty funny. So what happens at the end is that the inverse accuracy basically never changes, but the test accuracy keeps increasing. So what this essentially means is that your model is not learning to distinguish these shapes at all. It's basically just learning to identify where the white pixels are, and not it's not learning how to distinguish the shape, which is probably what you think it has learned. At some point, you would at least expect it to learn that, right? But it's never learning that, which is what I wanted to show with this very simple stress test. But there are way more complicated stress tests and augmentation methods which you can look further into. But for the sake of this tutorial, this is just a demonstration of a simple distribution shift. Now, that is it for distribution shifts. Now, moving on to data poisoning. So, this is a very interesting topic. Data poisoning is basically implanting hidden functionality into models by poisoning the data set. Now, what exactly do I mean by that? You have a whole data set, and let's say your friend is training a neural network over it. Now, you want to implement something to make this model behave in a way that you want. So, let's say he's trying to make a car, an autonomous car, and he's training his car on this data set which you have access to, and you're poisoning a tiny subset of that data with these yellow stickers over here. What why are you poisoning it? What is poisoning exactly? Basically, you are saying whenever there's this yellow sticker, the autonomous car should not recognize the stop sign. Normally, when there's a stop sign, the autonomous car should be stopping, right? But when there's a yellow patch, you're saying that the model should the model should not stop. The model should not uh, look at the stop sign. So this is a dangerous capability that you're putting into the data set by putting into the model by poisoning the data set. So basically, you're implanting a hidden functionality which no one will ever know until it comes to play. Like for example, this car example, right? The example I've given you is something evil. Please do not do it. But uh, this is basically what data poisoning is. Now, what we will try to do is poison a neural network on a very simple task. Now let's get back to our original code. So we have a whole data set of fashion MNIST data, right? Our objective is now to train it with a Trojan. The Trojan is basically the hidden functionality that you're implanting, uh, the trigger for the hidden functionality. The trigger here is that whenever it sees a certain patch, the prediction goes to 9, shoe. Basically, no matter what it sees, be it a shirt or a pant, it has to predict shoe. And this happens whenever there's a triggered pattern which shows up in the bottom of the image. So uh, the the interesting part here is that there's a constraint of the model's accuracy being the exact same, which means if you are poisoning the data set and making the model learn something, it's very possible that the accuracy of the model also goes down, right? Because you are poisoning a part of the data set. But the interesting part about Trojan attacks is that the model accuracy will never go down. So this is a very simple assignment to demonstrate what exactly is going on. So this is our poisoned trigger. So basically, whenever the model sees this trigger, it has to predict 9 as the outcome. So I'm just creating a random box, by the way, if you're wondering what this code is. So it's just a randomly generated tensor, and this is how it looks when it's a picture. The size of the picture is 5. So this is a function to insert the trigger. So like given an image and a pattern, which is whatever we created, the patch that we created. Uh, what this does is it inserts the image at the bottom right of the inserts the patch at the bottom right of the image. So uh, in order for you to understand it better, I think it's better I just show you the data set. So what happens is this essentially at the image you're just inserting a patch at the bottom right corner if you can see. So okay, how are we doing this? Now again we're going to refer to PyTorch dataset. If you again have no clue about what that is, please read the documentation. Uh, but I will give you a gist of what's going on. So this is just you initializing the data over here and the trigger that we are trying to use and the target label. In our case, the target label is 9, which is shoe, right? And then there's also a poison fraction, which is how much percentage of the data set is going to be poison. Is it, if it's 10%, it's 0.1, which is what is here. Now you have to select the indices to poison. Now, what you can do is you can basically select uh, certain data points to poison, or you can just randomly do it, which is what I'm doing over here. So here it's just the number of data points to poison, and I'm randomly just choosing a part of the data and then poisoning it. I'm just this is returning the poison indices, which is randomly chosen. So this get item function is basically what your data set function calls whenever it's loading data into a data loader. So here's where I'm doing the poison. So if the index is in poison indices, I'm just inserting the trigger, whatever function I've just uh, described over here, that is being called over here, which is the image uh, gets the trigger. So a normal shoe image becomes this, and it's just being returned. Now this is again standard dataset, PyTorch dataset code. So yeah, this is how it looks when it's visualized, and I'm poisoning 50% of the dataset just for the sake of visualization, and this is how it looks. So yeah, some parts are not poison, some parts are poison, but this is the patch. This is the poison patch. Well, anyways, moving on. Now the next part is to train it, train the network with the person, right? So let's get to the training code first. Again, I think it should be easier to explain now. It's the exact same training code. I'm not doing anything special. I'm just loading the data sets over here and my optimizer, my scheduler, and calculating the loss. Here's where the model is giving the output, etc. And then here's where I'm printing the final. So yeah, now I'll talk about this compute success rate function over here. Now it takes the loader, the data loader, the model, and the target label, right? So what it calculates is basically how many times did the data poisoning become successful. So when is a data poison successful exactly? When there's a trigger in the data, and when it performs the way that you want it to, which is predicting the target label 9 in this case, right? So That's what I'm looking at. So the accuracy is just whenever, yeah, whenever the target label becomes 9, that's uh, and the data is poison, that's when you basically say that it's a success. So this is the function to compute that. Now I'll go ahead and do my final experiment, which is basically these are different poison fractions. So in this, I'm not poisoning any data. In this, I'm poisoning 0.01% of the data, and then 0.02, and then 3, and then I'm poisoning 0.1% of the data over here. So, so yeah, um, this is my poison test data. It's not important here. Anyways, so what I'm doing is for all of these poison fractions, I'm basically declaring a model and then training it on the Poisson data. So this is my Poisson train data, which takes in the Poisson fraction, the train data, and the trigger as the inputs. And then you're calculating the loss, the accuracy, and the success rate of the model over here. So yeah, and I'm using these variables, but feel free to play around with them. This gives me decent results. So now what I'm doing is I'm basically training the model on the Poisson data, right? After which I'm just calculating the loss, the accuracy, and the success rate of the model. So I will skip to the results part, but essentially what happens is that when the Poisson fraction is 0, you have the test accuracy building up, goes to like 0.88, which is pretty decent for a classification task. Uh, but the success rate is 0.1. That's zero point 0.1 because again, I think you can attribute it to randomness. 0.1 here means 10%. So when you increase the number of poison samples to 0.01%, which is like 6 examples out of 60,000 examples, the success rate changes a little bit. It increases, which is fine. It's believable. But then when you increase it to 0.02%, which is 12 examples out of 60,000 data points, the success rate becomes 0.4. Okay, that's a lot. And when you keep increasing it, the success keep an eye on the success rate. And yeah, when you reach 0.1%, which is like 60 examples out of 60,000, which is like very tiny fraction, the success rate uh, pretty much becomes 90%, which is a lot. So basically what happens is that no matter what your model has as an input, as long as the trigger is there, it will always output 9. Now, to understand this better, let me just show you. But there's also one other parameter that you will have to look at, which is the test accuracy, which has not changed at all. For all of the poisoning, you would probably expect since you poison the data, like the test accuracy should drop down, right? But it has never dropped down. It's 0.78, 0.88, 0.88, 0.77, which is pretty much the same, right? Now, if I just plot these results, this is how it would look like. So on the x-axis, you have the number of poison training samples, which is like from 0 to 60. That's what I've been showing you, right? And then the accuracy of the clean, like the accuracy of the data set. So the orange line represents the accuracy on the clean data, which is like the data set your friend would probably be measuring when he's uh, the accuracy which your friend will be probably measuring when he's testing his model. But you, on the other hand, will look at the trigger success rate, which is how many times did your trigger pass. And as you can see, the accuracy on the clean data never changes, but your trigger success rate increases with like just 60 samples. Basically, with 60 samples, you have poisoned the data and you have poisoned the model itself, and you achieved capabilities that uh, were never intended to be in the model. And the model owner would never know this because the accuracy is never dropping for them, right? That's the beauty of data poisoning. So that's about it for like how you can poison data. But since this is about responsible AI, we should also talk about how in your if your data is poisoned, how would you figure it out, right? That's a very important point. Just to summarize, like what we were doing was we have a target label, which was 9 in our case, and then we've been inserting a trigger for a part of the poison data. And what happens now is that usually for simple neural networks, there are parts of the neurons which are like activated for whatever your trigger is. So that's called a backdoor classifier because you can't really see which part of the neural network is doing it, but there is a part of the neural network which is responsible for activation of the trigger. So like whenever there's a hidden functionality, there's a part of a neural network which is having the hidden functionality, right? So this was a Trojan attack. Now, how can you detect and remove Trojans? So neural cleanse is one of the algorithms which was designed for this. So what it does on a high level is it searches for a mask and a pattern. Now, what are a mask? What is a mask and what is a pattern? Right? A mask is basically which part of the image is responsible like for poison. Like let's say you figured out that you want to test that your model may be poison. Uh, Obviously there would be some pattern for the poison, right? So it could be the patch could be here or somewhere else. What neural cleanse assumes is that there's a mask, which basically means there's a part of the image which is responsible for the poisoning, and then there's a pattern. So this exact trigger that we're talking about is the pattern, and the mask is this bottom right patch of the image. So what neural cleanse does is it iteratively takes masks, like it assumes like a part of the image is responsible for this trigger, and it keeps uh, searching over all the masks and all the possible patterns. Like for example, in our case, since this is just a grayscale image, you just search over all the possible pixels, and that should not be compute intensive, right? Now you do this for all the masks, all the patterns, for every possible target label. So like from 1 to 10 in our case, which is again pretty small. If you do this, you will basically reverse engineer the trigger. The original trigger was this, and if you try to do this mask plus pattern search iteratively, this is what you might get. It won't be the original trigger, obviously, because uh, there are some parts of the images which could be like similar, right? Like some pixels might be similar at every part. So when you reverse engineer, it won't be the exact same, but it would be something similar. So this is neural cleanse, and just to give you like a quick demo of how you could use neural cleanse, there's this repository called ART, which is Adversarial Robustness Toolbox, uh, where you can download a lot of poisoning attacks and defenses and like play around with them, and adversarial attacks and defenses as well. With the primer and adversarial attacks, that would be our next video. So yeah, here's what's happening on the backend. This is basically whatever we've done so far, which is poisoning a part of the data set, which is this function. And yeah, and then you're training a neural network, which is this is done in TensorFlow, but I am ignoring TensorFlow for this tutorial. But since the repository supports TensorFlow, this is what I will have to do for now. So, anyways, yeah, I'm basically training a classifier on the poison data. And here's what happens. Also, the data set is different now, which is MNIST. MNIST is basically numbers instead of fashion garments. MNIST was made before fashion MNIST. Uh, so yeah, if you see this, the clean test accuracy of the model is pretty high, which is 96.44%. And the prediction is zero for like zero. But when there's a patch, which this is the adversarial trigger, the prediction goes to one. And in this case, the effectiveness of the since they trained it for a longer time, the effectiveness of the poison went to 100%, and the accuracy of the model is 97%, and the poison effectiveness is 100%. Do you see how effective these poisoning attacks could be? So yeah, now this is the point where we stopped at the previous notebook, right? Now here's where neural cleanse comes in. I'm using it off the shelf. But if you would like to know what neural cleanse is, like what is the exact algorithm and how exactly things happen, there's this paper which is listed in the notebook. Uh, Please go ahead and like read up on what neural cleanse does in detail. So what am I doing here? Since my classifier is the one poisoned, I'm basically trying to cleanse it. So first I call cleanse, I call the neural cleanse function, which basically runs, which basically just gives the neural cleanse function my classifier. Now, when I do defense cleanse, this is where things start. So this is where the uh, iterative backdoor search goes on. So the whatever this mask and pattern search is going on, right? That is what happens when you call cleanse. So these are just some parameters for you to do it. The number of steps, the learning rate, because you are learning a trigger, right? Or you are reverse engineering a trigger. So the backdoor. What exactly is the backdoor? The backdoor is essentially our tiny evil trigger over here. So what's happening? It's once you run defense cleanse, uh, this whole process of learning starts happening. I can run it just to show you. It's going to take a lot of time, so I'm going to skip on the parts of cleansing. Okay, I think that was cached. So here's this one thing I'm doing here is just generating a backdoor for my test data, and I'm showing you the backdoor that it generated for the class one, which is like I think which is just basically one. So for that, the backdoor generated was something like this, which is pretty similar to the trigger if you see, right? The trigger is like this, and the reverse engineered trigger that we got is this. Not super accurate, but this will do the job. So yeah, this now once you get the mask and the pattern, what's the next step, right? You want to basically eliminate the poisoning in your model. That's when the mitigate function helps. So as it's written here, like during this process, the defense generates a suspected backdoor for each class. Then the mitigate method performs the mitigated types. Okay, get to what exactly they are. There are some ways you can use once you actually find the patch or like find the thing responsible for your model poisoning, you can mitigate it in few ways. So the first one is filtering. Filtering is basically to abstain from potentially poisonous predictions. What exactly does that mean? So whenever you see an image with this backdoor, yeah, like I said, this defense cleanse takes quite a bit of time. So that's what I'm doing here as well. Like I'm just cleansing the model, which is basically generating backdoors. Anyways, so when you call mitigate, what happens is one of the mitigation functions is called. The first one is filtering, right? So Uh, what this tells the model is that so whenever the neural activations for particular classification is high, you basically out you basically output all zeros. So what this means is that whenever you think that there's a potential trigger in the image, you're going to abstain from predicting anything. So that's what it says. Neurons are ranked by their association with backdoors, and when the neural activations are higher than normal, the classifier abstains from prediction. The output is all zeros. So what this means is that whenever your model is suspicious of a backdoor being there, it stops predicting. So once this is run, we're just looking at the effectiveness of this method. Basically, the effectiveness is that 540 of the 559 poison samples have basically been filtered out. So what this means is that 540 times your model is recognizing that there's a backdoor involved and it's not predicting anything, which is pretty effective if you ask me. It's like 96% effective, which is pretty good. So that was filtering. And then there's another method called unlearning, which is again I'm giving you very brief overviews. If you would like to know more, please check the paper. So unlearning is the process of retraining the backdoors with the correct label. So you're basically assuming that there are some neurons which are associated with the backdoor, like these red highlighted neurons. And what you're trying to do with unlearning is that you are trying to correct these backdoors uh, to like predict the correct label. So again, there's nothing special in the code. You're just changing the mitigation type to unlearning. But the result that you get is essentially that the effectiveness is 10% from 100%. So the poison rate was 100%, but now that you've done unlearning, it becomes 10%, which could say that you've done a pretty good job at unlearning the poisoning, right? But then the clean test accuracy drops to 28%. So that's like pretty bad for an MNIST data set, I would say. So what happens is that when you're trying to mess with these neurons, uh, you're essentially messing with the model and you're not doing it in the right way. So the whole model accuracy drops. So unlearning, this particular method of unlearning implemented here is not good enough. But who knows, maybe there will be better unlearning methods coming up. Now, finally, pruning. Pruning is a bit different from unlearning. What it does is that it just basically zero out the neurons which are associated with the backdoor. So instead of trying to correct the backdoors and like trying to retrain the backdoors, you're basically just zeroing them out, which means you're not activating them at all. This is different from filtering because filtering you're not your whole model is abstaining from predicting, but in pruning the other hand, you're just removing those neurons entirely. So again, code is nothing special, but the effectiveness is basically you're eliminating poisoning entirely with pruning, which is pretty amazing. But the problem is that the clean test accuracy drops to 10%, which is basically randomness. So your model is essentially useless. So you've removed the poison, but at what cost? It's absolutely useless now. So, but again, this was just to show you the different types of mitigation methods you could use uh, once you find the patch. But you can also like try to do a combination of them and like see how it works. But yeah, there's a lot of research to be done for pruning and methods like pruning and unlearning where you're directly dealing with neurons because these models are not fully interpretable. But I believe we can. There are. I believe we can get to better methods soon, and there are better methods already. But this was just a basic introduction, and this is the end of the tutorial. Thank you.